And then just kind of like a general study, just to kind of tie this off, a large scale study of programming languages and code quality in GitHub. And so what I liked about this one is that they did a very large study on GitHub to determine whether languages and things like static typing, strong, weak, dynamic typing, things like that had an impact on the code quality. And what does code quality mean? Now, I also am not actually convinced that this is a very strong study given the methodology they used, but I do think that there are some insightful things in the study that we can kind of extract from it. And this will be the last thing I look at for the stream. So just one sec. I gotta have some more coffee here. Man, all this talking. Listen, a few W's in chat for me for being the guy who's falling on the sword here. To do all these, to reading all these studies and reading all this data and putting it together for you so I can try and make the industry better so we can all make more money. W's in chat for me, okay? No one else is doing this for you. Okay, so what is the effect of programming languages on software quality? Thank you, folks. Thanks, Al, man. Literally, I do not see anybody sitting down on stream and going over scientific studies to try and prove an argument. And the argument being we can all make more money and do better software and web. I just don't see it. At least I'm trying. Even if I'm wrong at the end of the day, at least I'm trying. This question, okay, blah, blah, blah. Okay, so in the study, we gather a very large data set from GitHub. This was impressive. Thanks, Travis. Appreciate it, man. 729 projects, 80 million lines of code, SLOC, I think single lines of code, 29,000 authors, 1.5 million commits in 17 languages. If nothing else, just those numbers alone are impressive for this study. This reasonably large sample size allows us to use a mixed methods approach, combining multiple regression modeling with visualization and text analytics to study the effect of language features such as static versus dynamic typing, strong versus weak typing on software quality. Okay. So essentially, we report the language design does have a significant but modest effect on software quality. Most notably, it does appear that strong typing is modestly better than weak typing. And among functional languages, static typing is also somewhat better than dynamic typing. We also find that functional languages are somewhat better than procedural languages. Man, where's Tej, Where's Leo? Who else? Mulroy? It is worth noting that these modest effects arising from language design are overwhelmingly dominated by the process factors such as project size, team size, and commit size. However, we hasten to caution the reader that even these modest effects might quite possibly be due to other intangible process factors. For example, the preference of certain personality types for functional, static, and strongly typed languages. Right. So then what they do is they go into a breakdown of their like methodology and languages. So we choose the top 19 programming languages from GitHub. We disregard CSS, shell script, bad cop would not like this, and Vim script, as they are not considered to be general purpose languages. Oh, damn, shade thrown. Oh, I want to... Oh, I got to put that. Hang on, I got to put that on X. I'm putting it on my X. Shade thrown. We further include TypeScript, a type superset of JavaScript. Then for each of the studied languages, we retrieve top 50 projects that are primarily written in that language. Table 1 shows top 3 projects in each language based on their popularity. In total, we analyze 850 projects spanning 17 different languages. So here we go. I'll just zoom in on this, but you can see what they pulled. So they've got C. They literally looked at Linux, Git, PHP source, C++, Node WebKit, PhantomJS, Mongo, C# mentioned, Objective-C, Go, Java, CoffeeScript, CoffeeScript, JavaScript, TypeScript, Ruby, PHP, Python, Perl, Clojure, Erlang, Haskell, Scala. Okay, so not bad. Not bad. Except that for TypeScript, look what they looked for TypeScript. Remember? Boys, do you remember? Remember? Dojo, how do they measure or define quality? Also, too large of a sample is bad statistical practice. If you're capturing a lot of experience, your study is flaw. I'm a math guy. I guess we're going to get into we're going to get into what they consider quality, and we'll see, because I'm not sure that I agree with their definition of quality either. So they retrieve the popular projects, then evolution history. And so you can see that what they did is they looked at like overall history so that they could kind of determine which projects had a overall history that kind of like lined up really well with the kind of study that they wanted to do and the data that they were looking for. So, okay, like not bad, not bad. Then they categorized the languages. And so you can see they did things like procedural, scripting, functional, static, dynamic, strong, weak, managed, unmanaged. Also good. I think this is a good thing to do. The project domain, also a good thing to do, right? That way, if you're going to look at the data, you can kind of break it out by kind of like these domains and types. I do like that. Then they categorized bugs. So while fixing software bugs, developers often leave important information in the commit logs about the nature of the bugs. For example, why the bugs arise and how to fix the bugs. We exploit such information to categorize the bugs, similar to Tan et al. First, we categorize the bugs based on their cause and impact. So root causes are further classified into disjoint subcategories of errors: algorithmic, concurrency, memory, generic programming, and unknown. And then they break it down even more. Keyword search. This is one of the things that I thought was kind of iffy. We randomly choose 10% of the bug fix messages and use a keyword-based search engine to automatically categorize the messages with potential bug types. I mean, I don't really know if I like that. It kind of sounds to me like somebody could, like, you couldn't exactly tell where a bug fell into, and you maybe you didn't have the expertise on hand in the study to determine it. So you kind of made like, you kind of had to bucket them. I can understand why, if you don't have the expertise to actually like determine these things, you might choose to make this approach. But I find this approach a bit like there's a crack in the armor here, right? And this is probably just one of a few. So then they go on to talk about bugs, and then they go and they categorize them in terms of the proportion of precision versus recall, right? So like what kind of bugs they are, and whether or not they appear again, or whether they get fixed, etc. Right? And so you can see the breakdown. Concurrency being, it looks like concurrency is like the highest one. So then they go through their statistical methods, and so you can see in terms of bugs, etc., what they go through. So let's just have a look at some of the warnings. So I remember reading this part. So there are some differences in terms of, are some languages more defect prone than others? And you can see there's some deviancy numbers here that might like indicate that there would be, right? So down here, right? You might look at these numbers, and some of these numbers might be like, oh yeah, clearly like something is objectively better than the other thing. However, they do make an important note that I think is important. One should take care not to overestimate the impact of language on defects. While these relationships are statistically significant, the effects are quite small. In the analysis of deviance table above, we see that activity in a project accounts for the majority of explained deviance. So it actually isn't so much the language that's being used, although it has some impact on whether or not there are defects in the language, it's actually more about the activity. And that kind of makes sense to me, because the more activity you have, whether you have a good language or a bad language, you introduce like a higher set of code changes or code numbers or whatever, lines of code, where defects are more likely to appear, rather than a probably more consistent rate of defects if you introduced very, very little and you just accepted whatever defects came with the language itself. So, that's an important thing to note. So then some languages have a greater association with defects than other languages, but the effect is small. So that's kind of like their first result. Which language properties relate to defects? So now we're looking at like language properties. So then you can look at things like defective commits, for example. So what they would do is they went through commits done for each project, and they determine which commits of which type, and they put that in a bucket, like type of commits, and then they determined whether that commit led to a bug or a defect. And so then what they could do is they could provide a number that looked at essentially the type of defect, so defective commits, and then how they impacted the number of defects that came out, overall. So you can see things like log commits versus, say, proc static strong managed, procedurally static strongly managed. I think that's what that would mean. And then functional static strong managed, right? Like there's a difference there, right? So then in terms of results, there is a small but significant relationship between language class and defects. Functional languages have a smaller relationship to defects than either procedural or scripting languages. And you could probably come up with a few reasons why that would be the case. Does language defect proneness depend on domain? So the middleware domain, JavaScript, is the most defect prone, 31%. This was little surprising to us, since JavaScript is typically not used for middleware domain. On a closer look, we find that JavaScript is only one project, V8, in middleware domain that is responsible for all the errors. That's pretty damning. Also, Scala is the most defect prone in the application domain, with a defect density of 52.67%. However, a single project, Zipkin, with defect density of 80% contributes to most of the defects. Similarly, Perl and C are the two top most buggy languages in database domain, with defect proneness 58.63% and 61.47% respectively. However, we find that the MySQL project is solely responsible for such a high defect count, where overall defect density of MySQL is 70.25%. Thus, it turns out the variation of defect density of the domains with languages may be an attribute of individual projects. And so then they took an approach to try and filter that out to see, could they filter out individual projects versus not. There is no general relationship between domain and language defect proneness. It's probably more related to the project itself and the nature of the project. So even though you could look at a statistic to say, oh, look, this domain is sucking, it actually might not be. What is the relation between language and bug category? So then they describe what they use for that. So here you have the bug type versus the class, like the type of code base that they're looking at. So you can see the strength of each bug type given the type of class of programming language. So some of them are clearly going to lean more towards a particular bug type than others. And you can see that the functional languages kind of have it better overall, I'd say. Kind of have it better. But I think there's some that stand out here and some that don't. And then you have programming errors. So they define like what these are. There's programming errors. There's so then they go, generic programming errors account for 88.53% of all bug fix commits and occur in all the language classes. For example, we find 122 runtime errors in JavaScript that are not present in TypeScript. In contrast, TypeScript has more type-related errors since TypeScript compiler flags flag them during development. Memory errors account for 5.44% of all the bug fix commits. Right? And you can see, this is kind of interesting. You can see the type of like the language versus the type of issues that the language has. C, taking the lead on memory. Well, let's have a look at like what would be the worst offender. Maybe Go on concurrency, perhaps. If I'm reading this right, it might be the other way around. But yeah, like, yeah, I can actually kind of see this being generally true. I can see why JavaScript will lead to more particular types of errors than TypeScript, and TypeScript will lead to other types of errors. But this is an interesting one. Though Java has its own garbage collector, having a memory leak is not surprising since unused object references often prevents the garbage collector from reclaiming the memory. In fact, we notice 28.89% of all the memory errors in Java come from a memory leak. 1.99% of total bug fix commits are concurrency errors. And then they break down the languages that have almost a direct effect on this. Around 7.33% of all the bug fix commits is related to impact errors. Among them, Erlang, C, C++, and Go produce more security errors than average. This does not surprise me at all, actually. Defect types are strongly associated with languages. Some defect types, like memory error, concurrency errors, also depend on language primitives. Language matters more for specific categories than it does for defects overall. Then they cover related work, probably stuff they've referenced. And then they make some small conclusions, which we've already covered. So that's the kind of the last thing I wanted to touch on this stream.